Flex emotion, the fire emotion. Personally, that's how I responded when I killed like a couple of
Are you gonna hold it?
Right.
Okay. Thanks. Thanks, Twig. Appreciate it.
I thought he was. No, Jacob's Twiggy.
They're interchangeable.
Yeah.
So I have KSU, Twig, and Twiggy. So,
Okay.
there you go. All right, so here's what you should see, okay? On the pink sheet, lavender, whatever you want to call it. So if all goes well, like on C, where you're given A and B in those concentrations, what will be the initial rate of disappearance of A, that should start with a 4 and be something times 10 to the negative 4th. Okay? Speaking of 4s, the rate constant K on that second one with the nitrogen monoxide and bromine should be something times 10 to the 4th. And make sure that you have the units, because I am going to your units are absolutely vital on this unit. On the circled problems, on number 19, your first answer on that rate of formation of B4 should be something times 10 to the negative 4th, and the hydrogen should be something times 10 to the negative 3rd. Okay? It's easiest if you do the stoic. If you want to look at it in terms of like what I have on the sheet where you put like 1/4 and then the change in concentration of pH3 over time equals, if you want to do that, you can, or if you just do stoic, it doesn't make any difference to me. On 23, and I left this in terms of minutes because that's what it was in. On 23, that rate constant should be around half the number of degrees in a circle.
Degrees interior of the triangle.
Or the sum of the in Euclidean geometry.
You had to do that.
On 24, you should see that they are first order with respect to both of the reactants. And on 27, if you leave it in micromoles per second, Charles,
Yeah, Charles.
your answer, because they all kind of build off of each other, that answer on 27D in micromoles per second should be an at best GPA.
Okay.
Or a horrible one, depending upon your perspective. Some people would be happy with that. It's an indexical.
You can't graduate with that, can you?
You can graduate with that. D's get
I
degrees.
got .28.
I think it's have a 3.0. Oh my god, wait, no, I'm lying.
D's
I was
get
thinking,
degrees.
I was thinking, I don't know.
Bare minimum, baby.
Yeah.
Never mind.
D means done.
D means done.
D means done.
D minus, baby.
I was thinking a 3.0.
So hey, aim high.
Bare minimum.
Aim
I was
high.
thinking 5.0.
All right, any questions on that? Are we good? Once, twice, sold. Get that
That
handed
was the
in.
easiest. I know. Well, actually,
Do you
I lost
want,
my
Berg, what order do you want it?
Purple sheet on top, white sheet, work.
All put them together.
Purple, yes. Yes.
Oh, it's right. So it's
All the safety.
White sheet. Not racist.
Wait, did I do it right? No.
No, you didn't do it right.
It's not hard. It should be malaria, say malaria, because if last people one where, why is last where? So two.
I
One,
Accelerated
malaria,
I was so mad.
Use this in, you saw this.
Okay, I said no. I couldn't see a single one of your showers.
Back
But I
there
can't even
was
think
the
about
car.
it. I wasn't even on the field, and I'm like,
Around.
no, I think.
and then one over malaria, and then.
Maybe I didn't think I was here that day. And I didn't want to
Schrodinger's cat.
close it. They closed it. Like, probably would have really set off within 20 minutes. So I didn't. I watched them now. Your hanging stapler's out of the This public is on now.
A great trip.
Hello, Mr. Backhand. Hey, you're Sean, you did say something. Good job. Hello, Mr. So pleased, though. Why is he just air?
What'd you get? What'd you
Before I was in like your classes, I would watch your Indian lectures for fun.
That's,
I was too high.
Oh, I don't have a pencil, that's why I was.
I'm down.
how can you put it upside down?
What do you mean? You
A
just
little
put it
bit.
upside down. There we go.
And that's not water weight, I'm still drinking.
You just.
Look, he's really good at math. Okay, let him be really good
You
at
can see
math.
my.
How can you put staplers in upside
I
down?
don't know. It
With a
didn't close,
publicized
so I figured I was upside
I
down.
was, after the last power line, right at the start of spring break, I was
His first
208
assumption was to blame
that
him.
night. And I was one
This is why I'm.
Where's David working?
I'm not dead.
There we go.
Oh, it's
I'm
red
telling you, I'm not even
everywhere.
moving anymore.
So red.
My
They get mine for us.
was 2 more legs and 2 sheets.
Why do you hate Morgan?
I'm so wrong.
Okay, Kevin, are we still going or start that back out?
He doesn't know about
We're
that,
gone.
because that's
Okay.
Oh, they
All
just saw.
right, so again, break out yonder sheet
And
of
we have to
lecture
make it
notes.
one more day.
Oh, lecture notes.
So, what we dealt with yesterday was what's called, it's technically called the differential rate law, but everybody just calls it the rate law. Now, it's cool in the sense that it's fairly simple. Like, you have something like R equals K times the concentration of A or hydrogen or whatever that is, okay? And it's cool if you know what that K value is, and if you know what that initial concentration is, you can determine what that rate is going to be, okay? If it's a big number, the reaction is going to happen very quickly. If it's a small number, the reaction is going to take place slowly, okay? But here's the downside to it. It's a one-trick pony. It's a good trick, but it's a one-trick pony because this is only valid when that concentration is at a particular point. Obviously, when reactions happen, concentrations change over a period of time. Concentrations go up, concentrations go down. So if your concentrations are continuously changing, that means, okay, hey, what impact does that have on the rate? So from that, you can get what's called the integrated rate law. So this is the second column down below. So what we're going to focus on are zero, we're not going to worry about zero order reactions because they're so rare. We're going to focus on first order and second order. So if you look at first order, you have the natural, and if you're a math nerd, this is going to speak to you because this is natural logs, okay? Plus the natural log of A naught. And if it's second order, gap, then it's 1 over A equals KT plus 1 over A naught. Okay, so now there's a couple of things that are important.
How brave am I today, Bird?
I think that's an
No, just
no.
answer the question.
I think
please.
the question is how stupid are you today?
You're very stupid. He's saying yes. Please no. Please no.
We'll see what happens.
Yeah, that's all you, buddy.
Cohen?
Yeah?
If if I have to come over there.
You don't have to come over here. You
I'm
should
not,
accept.
I'm not responsible for what happens to that laptop.
Don't worry. Just laptop is the least of your problems.
Then close that laptop.
I'll need. You should look at your TV real quick. Click accept, Berg. Do it.
Oh, great.
Oh,
Now you're
cursor.
gonna need class
It's a
time.
cursor.
Block.
No! Why would you do that?
You should have blocked
You
it.
should have blocked.
So Cohen can never.
How does use Jake's computer now? No.
Okay,
You just hit decline. He didn't block you.
anyway, back to our story. So you have to see where these all fit together as well. So this is the integrated rate law version of this. The rate law itself is R equals KA. Now, these two have to fit together in terms of units. And I'll show you why this works. So any rate is going to be measured in what units?
Molarity per second.
Molarity per second, right? Here's the concentration in molarity, right? So K has to have units of what? 1 over seconds, okay? So K from the rate law equation has to have units of 1 over seconds. Cool with that. Now, when you get to the integrated rate law, here's the cool thing if you don't like units about natural logs. As soon as you take the natural log of something, the units disappear. Okay? It's the only time this happens. You take log, natural log, just trust me.
Why?
The units go away.
There has to be a reason.
Because it doesn't, you can't have like the natural log of molarity. It just doesn't make any sense. Okay? Just trust me, go with it. So what this means is that once you take the natural log of this, it has no units. When I take the natural log of A naught, and A naught means the initial concentration of whatever that is. So A naught just means the initial concentration. That has no units. So what that means is that this right here also can't have any units. I can't try and add something that has units to something that doesn't have units. So this is why, if you look at the K, even in the integrated rate law, that K is going to have units of 1 over seconds. Because then when I take 1 over seconds times seconds, the seconds cancel out and it has no units. Okay? So whether it's the rate law or the integrated rate law, the units of K are going to be 1 over seconds. Now, the same thing is going to be true if it's a second order. If it's second order, you have R equals K times A squared to make it simple. So if that's the case, this is molarity squared. Molarity per second has to be your rate. So what has to be the units of K? When I multiply molarity squared to get molarity per second, what has to be the units of K?
1 over molarity.
1 over
Seconds.
1 over molarity.
Molarity
seconds.
1 over molarity seconds?
Yeah.
Cool with that? Now, here's the story. This is going to be 1 over A, which is going to be 1 over molarity. So this unit over here is just going to be, you could either write it as 1 over molarity, or you can put it as molarity to the negative 1. This also has to be molarity to the negative 1. So now, what happens here is that once I take 1 over molarity seconds times seconds, the seconds cancel out, I get 1 over molarity, everything's the same, and I can add them together. So this is why no matter what, if you're working in the first order, if you're working in the second order, the units of K have to be the same, no matter which version of this you're using. So the advantage of the integrated rate law is that this involves time. Everything on this involves time. So what that allows you to do is end up with being able to make a prediction. So if you know what the rate constant is, and you know what the value of time is, you can sit there and go, oh, cool. I can calculate a concentration after a certain period of time. If I let this reaction run for an hour, what's going to be the concentration? If I let it, or if I say, hey, I want the concentration to reach a certain point, I can solve for time and go, oh, how long is that going to take for that reaction, that I have to let that reaction run to end up with this amount of reactant or product or whatever you want. So the integrated rate law is much more versatile because it involves time. The rate law itself is cool, but it's a one-trick pony because it only works with that particular concentration. I can't look at the rate law and go, oh, what's going to be the concentration 30 minutes later? I can't do that. But I can look at the integrated rate law and go, oh, what's that going to be after a certain period of time? Now, here's the other anomaly about this, is that both of these, even though it looks nothing like it, are all in the form of y equals mx plus b. These are all linear functions. And if you look at it, you're going, whatever. You've got natural logs and inverses and all of this stuff. But these are all linear functions just written in weird ways. So here's what's going to be important. So let's start with the first order reactions. So what this means is that when you draw the graphs, and this is going to be all about the graphs. So if it's first order, when you draw those graphs, and you're going to draw a lot of graphs, what that means is that you're going to plot the natural log of A over here, and then you're going to put time on the x-axis, okay? Now, here's how this is going to play out. Let's say that you have a slope like this, natural log of A. The natural log of your initial concentration is going to be your y-intercept, okay? That's what that means, that's your y-intercept. So if you know what that initial concentration is, then you can take the natural log of that, and that's what's going to get you that value. So if you look at this in terms of slope, this is where this becomes a bigger idea. Since this has no units, because when you take the natural log of it, it has no units. So if I try and find that slope of change in y over change in x, because I'm graphing natural log, which has no units, versus time, which is in seconds, then the units work out to be 1 over seconds, which is what the units of k have to be to make everything work out. So there's two ways that you need to understand, if it's first order, why it has the units that it does. Number one, that way I don't have any units on anything. Also, when you look at the slope, that's 1 over seconds, because natural log has no units. You have time on the x-axis, which is seconds. You end up with 1 over seconds. Okay? Now, the reason that there's a negative sign in front of this is because, and this will make sense once you actually begin to look at the graphs. Natural log versus time is going to have a negative slope. So that's why that negative is there. Don't look at that and go, oh, that's going to be a negative of a negative. The negative is just there to reinforce the idea that, hey, this line is going to be coming down like this. So don't look at that and go, oh, I need to take a negative of a negative. It's just the slope, okay? It's just going to be a negative value.
That's really, why did they do that for some and not for others? That's annoying. Just leave it.
Then ignore it.
But I can't, it's written.
Okay.
This guy.
Now, if it's second order, okay? If it's second order, then what you're going to do is you're going to graph 1 over A versus time. And those are going to have positive slopes. That's why there's a positive K there. Cohen,
Thank you.
you're welcome. Okay, now, if you look at the units on this, change in Y over change in X. Cool. So my Y value is 1 over molarity, and then my time is in seconds. And then that becomes 1 over molarity seconds. And again, that's why the units of K has to be 1 over molarity seconds. So then when I multiply it by seconds, I get 1 over molarity, which is what I need to have happen to make this whole thing work. Okay? Cool with that. All right? Now, the half-life equations. We'll go through the actual derivation of the half-life equations later. For now, I'm just going to point them out. So, half-life equations tell you how much time it takes for a reaction to run so that the new concentration is half of what it started with. So if your initial concentration is 0.5, your half-life is going to be how long does that take for that concentration to become 0.25. If it's 0.4, how long does it become 0.2? So that's what half-life means. So when you look at the first order, and tomorrow I'll show you where these come from. In the name of time, just accept them today. I'll show you where they come from tomorrow. So if you look at that first one, that time for the half-life is 0.693 over K. Now, because of the fact that this is a first order, what are the units for K?
1 over S.
1 over S. Now, notice 0.693 has no units. So then when I divide that 0.693, which has no units, and I divide that by 1 over seconds, the seconds flip up, I get time, that's what that's measured in. Okay? So again, it's consistent. It isn't like, oh, we're just going to randomly put numbers down and hope a miracle happens. No, it all fits together. Now, when you get to the second one, if it's second order, that half-life is 1 over K times A naught. It's the same thought process. So the K is in 1 over molarity seconds. You multiply that by A naught, which is molarity. The molarities cancel out. The seconds flip up. You get time. Now, here's the fundamental difference between a between the first order and a second order reaction. Your first order reaction is not dependent upon the initial concentration of the products. No matter what the initial concentration is, the half-life is still going to be the same, whether it's 0.4, 0.2, whatever, doesn't make any difference. And some half-lives are very, very long. Like, for example, on radiocarbon dating, the half-life of carbon might be like 6,000 years, okay? So some half-lives are incredibly long on radioactive decay. A lot of medicines, on the other side, have a very, very short life. Okay, you take ibuprofen. You have a certain amount of concentration of ibuprofen. Well, that half-life is very short because of the fact that it's going to get used up. That's the whole point of it. You don't want medicines with very, 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 very long half-lives. It's like, well, that really does kind of defeats the purpose if it's not going to get used up. Now, in contrast to that, is second order reactions are dependent upon the initial concentrations. So with second order, if your initial concentration gets bigger, what happens to your half-life? It becomes smaller because you're dividing by a bigger number. Okay? All right. So you got the background. So this is how these problems play out. So what you're typically given is a chart like this. And the only thing you're going to have is the time and the concentration. So let's look at this big idea. So at time 0, you've got 0.01. That's your A naught value. Okay, because at time 0, this was the initial concentration of A. 50 seconds later, it's dropped to 0.00787 as time goes by. Now, there's one thing when you look at this data. In this situation, it starts off going every 50 seconds, but then it changes to every 100 seconds. So when you are graphing this stuff, pay attention to the times. Don't assume that all the time intervals are the same, okay? Because sometimes they're going to change those time intervals, so be cognizant of that. So what you would have to do is literally take your calculator, and thank God for calculators, and you just punch numbers in. You would punch in the natural log of 0.01, and you would get negative 0.605, negative 0.573. You would actually generate those numbers. When you're generating those numbers, do not round them, okay? Don't look at that first one and go, oh, I'll just call that like negative 0.5, and I'll call the next one -5, and the next one no, okay? Keep lots of digits when you're getting those. Then you're going to take the inverse of those. Got that? Cool. So that's the first step, is that you have to generate the data columns. So what you are going to have coming out of a lab is literally a set of times and a set of concentrations. You have to mathematically derive and get those numbers. Now, this is where the graphing part kicks in. And I'm going to show you 2 ways that you can do this. And I promise you, I'm not going to walk in tomorrow and go, oh, here's the shortcut. You can just do this in one step, okay? You can't. The only way you can, Charles, really?
I just want a shortcut.
I know you do. Charles, shortcut. So,
Well, you're the tall guy.
kind of fits. So, the only way you can do this is to graph them. And sometimes, even trying to figure out which one is linear, sometimes that's a very, very small difference. So here's what you would have to do. So since I'm going to switch back to this other chart. Now, some people like this method of drawing this graph, okay? And I'm going to show you 2 different ways that you can do this. So you're going to come in here and you're going to go, okay, here's my graph. I'm going to have time here. And that's going to be 0, maybe like 100, 200, and 300. So we'll do, what?
Cohen is very loud when he eats chips.
He's a loud eater.
You always get like an entire lunch in this class.
Because he doesn't go to lunch. He doesn't go to
What
lunch.
do you do?
That's a good question.
Most of the time, this.
Okay. Now, if you're going to do natural log, we'll do that one first. When you do this, imagine that you're starting up here at 0, because your natural log is going to be negative values, okay? So if you look at that data, and kind of go back and forth between the 2. So if you look at that data set, you're starting up there at negative 4.6 all the way down to negative 5.5. So that's how you want to set this up. That's the advantage of starting at 0. So you're going to have 0, like -2, -4, -6 on this graph. So imagine you're starting at 0 and then you've got to graph negative values. So if you do that, and I set that up and went from like negative 4.6 down to negative 5.6. Okay? All right? And then I got like negative 5 in between. So with this one, and then you come in here and you plot these points. And that's what you would have to do. You're going to come in here and go, okay, hey, 50 seconds, boom, you got these points. And so you're going to plot those points. And then, and literally, like I said, Charles, there's no shortcut to this, okay? You just have to draw that line, okay? And sometimes, and the data set you guys are gonna have, it's gonna be pretty obvious which one is linear and which one isn't. But sometimes when you're working with like real data, it's kind of like, which one, you kind of have to decide which one is more linear, okay? Because it might not fit this exact precise line because of the fact that, hey, welcome to science, and you might have imprecise data. So this is why, Cohen, if it's first order, this is why the slope is negative, because of the fact that you're plotting negative values for that natural log, okay? Does that soothe your negativity towards negative k?
A little.
Okay. Now, here's where some people like this and some people hate the next option. The next thing that you could do is come over here and set up a second y-axis over here where you're going to plot 1 over the concentration. So with that one, and you can actually put like a little break to indicate that, hey, I'm going to have a big gap. And so when I did this, I did it like 150 to 150, all the way up to like 300. So then I'm going to do the same thing. But now, this is why some people hate this. Because I've got to go to 0, come over here, I've got a point, and then at 50, I've got a point, okay? And then you're going to have a line that's going to go like this, okay? Now, the advantage of this is that you only have to draw one time scale. The disadvantage is that you kind of you got to kind of geometrically look at two different scales. If that's going to go, oh, that's going to make my head hurt, then draw them as completely separate graphs. Draw one where you have the natural log, draw a completely separate graph where you do 1 over a. I don't care, okay? It makes me no difference. Put them both on the same one, put them on separate ones, I don't care. Doesn't make me any difference. Now, if you look at this one, if I were to actually draw that on a real graph, you would see that this graph is the one that's linear where it's 1 over a, okay? That would be the one that if I drew this on an actual graph, if you look at like when I actually did this, this is the one that's linear, which means it's going to be a second order. So at that point, once you know which one is linear, then you need to find the slope. Okay, well, what's the slope going to be? Changing y over changing x. It's just a calculated value, okay? That's what you have to do. This is why you have to have the slope. Now, you'll even run into certain circumstances where that line is basically going to be like a line of best fit. So, I don't care which points that you pick to find the slope, but they have to be on the line of best fit. You can't use your data points to find the slope unless your data points are actually on the line, okay? So you can't look at that and go, oh, this is the one that's linear, I'll pick these 2 points. You can do that if those points are actually on that line of best fit. If those points are not on that line of best fit, you can't use it to find the slope. Okay, so that's your sequence. Draw the graphs. Hey, which one's more linear? You find the slope. So in this situation, and if you look at the points that I did to find slope, I had 210 minus 100, and that was 200 seconds. So my slope worked out to be 0.55. 1 over molarity seconds. Okay? So that's my value of K. Now, at this point, we're kind of off to the races. Now we can do a whole bunch of things. So, now that I know that it's second order, and here's how I personally remember the difference between first order and second order. First order has natural logs, and natural log looks like a 1. So that's how I remember the natural log is first order. Okay, and then it's okay, well, if the actual log is first order involves that, then the other one has to be the second order. That's just how I remember it. Okay. So now that you know the value of the slope, you can do a whole bunch of things. So one option is you can look at and go, okay, hey, let's calculate the half-life. So if you look at calculating the half-life, because of the fact that this, we know this is second order. So then I'm going to go 1 over 0.55, 1 over molarity seconds, and that initial concentration was 0.01. So somebody run the numbers and actually let me know what you get out of this for this half-life.
181.8.
So call it 182. Now, here's the beauty of this, okay? Here's the beauty of it. You said it was 182 seconds. So, because of the fact that you're going to have all of this data, you said it was 182 seconds. So, look at this. You're starting off at 0.001, right? That's your initial concentration. It's 0.01. So, when this becomes half, that value of 0.05 is going to be somewhere in this gap between 0.00649 and 0.00481, okay? Which means my time has to be somewhere between 100 seconds and 200 seconds. So when we got 182 seconds, that fits in this gap. So that's the beauty of this, is that since you're going to have your data, you can go back and look and go, hey, does that fit with what I have? If you had gotten 342 seconds, that doesn't make any sense. Because 342 seconds, that's going to be a concentration well below the half-life. Okay? So don't be afraid to go back and look and go, oh, hey, does that make any sense? Now, here's the other thing that you can do. 1G, pick a number between 200 and 300.
224.
224. Okay. So now, you said 224?
Yes.
224 seconds. So what I can do is now I can figure out, hey, what's the concentration after 224 seconds? So I've got 1 over A is going to equal my slope, which we said was 0.55, and that's 1 over molarity seconds. 1G, pick 224 seconds, plus 1 over my initial concentration, which is 0.01 molar. So what you've got to do is that you're going to do all of this, okay? Sometimes what some people like to do, so they don't have to do this step each time, they'll take the inverse of 0.01. So if I take the inverse of 0.01, what do you get?
100.
100?
Yes. So good at this.
Yeah.
And 1 over m, right? So that saves you going through and recalculating that each time. Oh, it's just going to be 100. Now, you're going to get this side, but that equals 1 over a. So how are you going to undo that? Yeah, you got to take the inverse of it, because that isn't a, it's 1 over a. Now, before you do any calculations, okay, let's just think this through. 1G, pick 224 seconds. What that means is, because she picked 224 seconds, what does my concentration have to be between at that point? Yeah, it has to be somewhere between 0.00481 and 0.0038. If it's not, something has gone horribly wrong. So that's why I said you can go back and look at your data and go, oh, all right, does that make sense? Okay, does it fit? So what'd you get when you did the actual calculations?
.00448.
0.00 what?
448.
448. Okay? So if you look at your data, 0.00448, that's in that gap. Okay? So at least we know we had a fighting chance that we did it right. That's second order. If this had been first order, which is a huge if, okay? Let me kind of take you through the math. Because first order is natural log, negative KT. So this is where this gets a little bit weird mathematically, but not bad. So if you're going to do this same thing here, and you need to find A at some point, how do you undo a natural log? E, right? Okay. So if it was log, it would be 10. So if it's a first order reaction, you're going to get this number, okay? And then you're going to take E to that value to get that concentration of A at that point. Okay? Got it? Good? Okay. Shut down that camera for a second.